Hi everyone, today we're going to talk about topic 7.3, reaction quotient and the equilibrium constant. So the reaction quotient and equilibrium constant are two very similar concepts to each other that can be used in two specific scenarios. So let's take this sample reaction here. I have m moles of reactant A plus n moles of reactant B react under equilibrium, or can react under equilibrium, to form x moles of reagent C plus y moles of reagent D. At any given time, during the reaction quotient is defined as the ratio of products to reactants in the reversible reaction. And so this is true at any given time of the reaction. So there's two different ways that you can find this value. The first is when you are given concentration. The symbol is QC, C meaning concentration, and that is equal to basically products over reactants. So you have the concentration of product C to the X power times the concentration of product D to the Y power, and this is divided by the reactants. Concentration of A to the M power, concentration of B to the N power. So if you want to find the ratio of products to reactants, you quite literally just take the ratio of those raised to whatever power you have here, right, raised to whatever the stoichiometric coefficient is. And so that's one way to find the reaction quotient. The other way is if you're given pressure, now it's QP, and for this, all you use is partial pressures. And so you'd have the partial pressure of C to the power of X times the partial pressure of D to the power of Y divided by the partial pressure of A to the mth power and the partial pressure of B to the nth power. So anytime you're doing these reaction quotients, it is always products divided by reactants. The only difference is what you are given. If you're given concentration, you use the top one. If you're given pressure, you use the bottom one. They are the same equation. It's just dependent on what kind of information you are given. Now, a very similar concept to this, as I said at the beginning, is the equilibrium constant. As you might imagine, this is only true at equilibrium, or when the rate of the forward reaction is equal to the rate of the reverse. And under these circumstances, Q is equal to K, uppercase K, where K is the equilibrium constant. And so at equilibrium, your reaction quotient is equal to your equilibrium constant. The equilibrium constant only exists specifically at equilibrium. And so you might imagine the equations are exactly the same. Kc, if you're given concentrations, is equal to the concentration, if you're using that exact same reaction scheme as before, concentration of D raised to the X power, concentration of D raised to the Y power, divided by concentration of A to the M and concentration of B to the N, specifically at equilibrium. There's a few different equilibrium constants with respect to concentration we're going to talk about, and I'll introduce them as we're going along. One is KSP. This has to do with precipitation. I've talked a lot about at some point we're going to be able to tell when something does or doesn't precipitate, and that's exactly what that equilibrium constant tells you. There's Ka, which has to do with acids, and there's Kb, which has to do with bases. And as we move on, we're going to be talking about these a lot more, but they all relate back to this right here, Kc. Similarly, Kp is the equilibrium constant with respect to pressure. So you'd have the partial pressure of C to the x power times the partial pressure of D to the y power divided by the partial pressure of A to the m and partial pressure of B to the n. And again, this is at equilibrium. And the only case when you use this is when you're given gases, if you're given partial pressure of gases. Now there's one extremely important consideration that I'm going to put down here. You all should write this down. Remember this. Extremely important rule. And that is that reaction quotients and equilibrium constants only contain species whose concentration or pressure can change. Can change. So what does this mean? This means no solids or liquids. If you have a solid or liquid in a reaction, that should not be included in the calculation for the reaction quotient or the equilibrium constant, which means only aqueous or gases. And that is going to depend on if you're using QC or KC, or QP or KP. Regardless, it's only aqueous species or gases. So let's just do one quick little practice so we can see what this looks like. I have this reaction here where I have Cl2 gas plus CS2 gas goes to CCl4 gas plus S2Cl2 gas. The first thing we need to look at is whether or not this is all balanced, and we can see that it is not. Here I have, on my right, I have 6 chlorines, and I have 1 carbon, and I have 2 sulfurs. On my left, I have 2 chlorines, I have 1 carbon, and I have 2 sulfurs. So all I need to do here is put a 3 in front of this to make 6Cl. Otherwise, everything else should be perfectly balanced. So now once it's balanced, I can actually write the reaction quotient for this. Now, we're not told what time point of the reaction this is at, but we're specifically asked the reaction quotient. So the first thing we think is we're using Q, because that's the reaction quotient. The other thing we need to look at is what is the phase or the state of all of our reactants and products. You can see they're all gases, and so we should be given pressure in a problem like this. So we're going to be using QP. The expression here is going to be the partial pressure of CCl4 raised to the power of 1 because there is nothing in front of it. Then it's going to be times the partial pressure of S2Cl2, again, raised to no power because it has no coefficient. That is divided by the partial pressure of Cl2 raised to the 3rd power because that is our coefficient, times the partial pressure of CS2 raised to no power. And so this would be the reaction quotient for this system right here, and you can calculate the ratio of products to reactants at any given time of this reaction. We'll discuss this more in class and have some more practice with it, but for now, that's all. Thanks, guys.